Welcome to our PLC Programming Best Practices series video. In this first video, let's learn how to improve our PLC programming using modular techniques. PLC programming may seem like just solving an engineering problem, but it's so much more than that. Sure, there may be multiple ways to program a PLC, and all of them might get the job done, but choosing the most efficient and manageable solution will save time and headaches down the road. Think of PLC programming as an art form. Our goal should be to select the best design among various options and make it clear, concise, and consistent for anyone who works with it in the future. Modules, whether in the physical or programming world, are individual pieces that can be connected to create a cohesive final product. By breaking down a program into smaller, more manageable pieces, we can simplify the program, we can reduce complexity, and we can make PLC program easier to test, maintain, and modify in the future. It's like building a wall with bricks. If we make the bricks one by one as we build the wall, it will not only be a time-consuming process, but the final product will also look unorganized and uneven. However, if we use standard size bricks, the wall will not only be stable, but it will also have a neat and aesthetically pleasing appearance. Similarly, using standard modules in PLC programming simplifies the process and makes the final product more organized, stable, and easy to work with. So think of standard modules as the standard size bricks of PLC programming. Let's take the example of motor control to compare the benefits of using modular programming versus non-modular programming. Consider a motor that has start-stop push buttons and a valve on its discharge. These inputs are connected to the PLC, and the PLC gives the start and stop commands to the motor control circuit. For our example, we will keep the inputs and program logic simple. In this example, the start and stop push buttons are wired to discrete input cards, and the start and stop commands are sent to motor control circuit through discrete output card. It is important to note that this video is designed to be PLC make and model agnostic. The emphasis here is on the principle of good programming practices, rather than how to program a specific make and model of a PLC. The goal is to provide a general understanding of how to apply good programming practices, regardless of the type of PLC being used. First, we will create logic in a non-modular way. For this, we will have to create tags for input and outputs for a particular motor. Let's take an example of a motor tagged M1. For this motor, there are 5 tags created. Now we will create a PLC program in ladder logic format. This is a very simple ladder logic. And if you're familiar with the ladder logic programming techniques, you could immediately observe that the start button will start the motor and the stop button will stop the motor. However, the valve limit switch should show the valve is open, otherwise motor will not start. This is very simple logic, and you must be wondering that this should not be a problem in developing a PLC program in this way. However, let's assume we have a lot of motors with identical logic. How we will scale our PLC program to take into account of all these other motors? Traditional approach will be to create tags for each motor. If one motor takes 5 tags, then 3 motor will take 15 tags. After tags creation, we will have to take care of logic for each motor. For this, we will have to copy and paste the logic for M1 and change the tags for each new motor. But this will be a tedious exercise requiring lot of efforts. Maybe you could get by if you have 2 or 3 motors. But just imagine if you have 20 motors with same logic. Programming in this way will be quite labor intensive. Now, I would like to discuss the issues with this non-modular approach one by one. The first issue is related to the number of errors that could creep in easily if you are not careful during programming. You may find that the best approach to create tags for additional motors is to copy and paste tags from M1 and then change and then point the tags to the new motor. But there is a good chance that we will forget to update the description or enter incorrect tag. See here, M3 is typed incorrectly in the description of M2 tags. To create logic for other motors, we will copy and paste M1 motor logic and change tags to other motors. With a large number of motors, we could easily forget to update some tags. During project commissioning, when time is of essence, problem like this could waste our precious time. Other issue with non-modular type logic is increased amount of effort that is required for addition of new features or logic to existing program. For our example, let's say that we now want to add start permissive condition to already created logic. We will have to insert this condition in right rung for every motor logic manually. You can well imagine that for large number of motors, this will be a bit challenging. In case there is a bug in PLC program, it will be very difficult to diagnose for non-modular logic. Non-modular logic will have large number of rows of code, and pinpointing the place where the error is will be tedious. We have seen that there are a number of issues using non-modular programming techniques. Now we will see how we could use modular style for the same logic and create a better organized program without these issues. For modular logic, we will use add-on instruction or AOI, and we will see how this technique will result in a much more organized PLC program. But what is an AOI? Think of AOI like a cookie cutter, except instead of cookies, it helps you create perfect shapes in your digital world. Imagine you want to make a bunch of cookies in the shape of heart. You could use your hands to try and make each one the same, but let's be real, they would probably end up as imperfectly shaped cookies. That's where the cookie cutter comes in. It's your trusty tool that lets you make identical shapes again and again. And that's exactly what AOI does. You put in a little time and effort upfront to design your cookie cutter, and then voila, you can use it to make all sort of perfect shapes and designs. It's like magic, but with technology. For PLC programming, our cookie cutter will be a self-contained block that will have all the motor logic and internal tags. Like a cooking baking process, we will develop this block once and we will use it multiple times. Here is the template for generic motor logic that is enclosed inside a block. Now, this is a template only and can't be directly used for a motor. We will declare an instance of this AOI for a specific motor and connect that instance with corresponding motor tags. Good news is that once AOI block template is developed, you could create as many instances as required. Each instance will have to be connected with a particular motor. It is just like getting free gifts once the AOI is ready. So this is an AOI instance created for M1 motor, and we named this as M1 underscore control and connected it with the M1 tags. So the nice thing about using an AOI is that we could create another instance of same AOI template, and we will name this as M2 underscore control, and we will connect this instance with tags for M2 motor. So we have taken care of problems of repeatedly creating the same code, but we still have to create tags for each motor. And the number of tags will increase considerably high as number of motors will increase. As an example, if there are 5 tags for a motor, for 3 motors we have to create 15 tags. With increased number of tags, there will always be a chance of accidentally connecting wrong tag with an AOI. As an example, here we have connected valve 1 limit switch to motor 3 control instead of valve 3. To better manage the number of tags, we will use another concept in PLC programming. This is called user-defined data types, or UDT for short. UDT is a great tool for organizing tags for a particular equipment. It is also called structured data type. In this concept, tags related to an equipment are grouped together and a custom data type is created. As shown here, here's a single UDT template named UDT underscore motor. It is created that contains all the tags required for a motor in our example. Now, this is a template only. Once this template is created, we could create as many instances from it as required, one for each motor. Using the template that we created, we have created an instance from it and named it as M1. Now this one UDT tag have all the component tags related to our M1 motor. Wherever we were using individual M1 motor tags, now we'll just have to use this one UDT tag and refer to individual components within it. The fun doesn't stop here, and we could create M2 and M3 tags in similar way. Notice that with this UDT, we don't have to create all component tags. We only have to create one instance for a motor and all the components tags will be automatically created. Now, how we will use these UDT tags? Here we will just have to point to the correct component when connecting with an AOI. As shown now, connections are M1.component. For example, M1.start push button is connected with start push button input. Start command is connected with M1.start command. This greatly simplifies the connection process as each UDT corresponds with an AOI of the same motor. Using consistent naming schemes will make logic better organized. This is how we will connect and use M2 UDT with M2 AOI. There is still a small possibility that we could accidentally connect wrong motor tag to an AOI as shown in the example here. To further improve our logic, we could use UDT inside an AOI. Let's see how to do this. If the PLC we are using allows us to use UDT inside the AOI, then we could create an instance of UDT inside AOI. Here we have created instance of UDT as motor that is based on UDT underscore motor template. In the logic inside AOI, we will use the motor UDT component tags. For example, start underscore PB tag, which we have used previously, it will now become motor.start underscore PB. So you can see now we only have to make one connection to this AOI. Now we could connect M1 UDT tag to motor UDT tag. Notice we have only made one connection. Individual connections will be automatic. The connections shown are made automatically. Notice we only have to make one connection, and as long as this connection is correct, we don't have to worry about the individual connections, as systems takes care of them automatically. Simplicity is the ultimate sophistication. This quote, attributed to Leonardo da Vinci, rings true in many aspects of life, including modular PLC programming. Modular PLC programming involves breaking down a complex system into smaller, simpler modules. By doing so, we can create a more manageable and maintainable system that is easier to understand and modify.